Algebraic structures, lecture 7, pre-groups and presentations. Let us start with a quick recap on subgroups generated by a set. Let G be a group and X a subset of G. Then we have the subgroup generated by the set X, which is usually denoted in this way, X in this kind of triangle brackets. And this subgroup of G is defined as the intersection inside of G of all subgroups H of G which contain X. Note that if X is the empty set, then the subgroup which it generates is just the identity subgroup, the trivial subgroup consisting just of the identity. In general, the subgroup generated by the set X consists of all possible finite products of elements of X and their inverses, and we can multiply them in any order. If we take all such possible finite products, it will define for us a certain subset of G, and this will be exactly the subgroup of G generated by X. Now we can talk in general about generators. Definition: a subset X of a group G generates this group G, provided that the subgroup of G generated by the set X coincides with G. Alternatively, one says that X is a generating system for some group G. For example, any group is generated by itself. So we can take X is equal to G, and this generates the group. Example 2. The group of all integers with respect to addition is generated by the integer 1. Because if we take the subgroup which 1 generates, it should contain 0, 1, 2, and so on. And also it should contain -1, that's the inverse of 1, the additive inverse, -2, and so on. So we see that the subgroup of Z generated by 1 coincides with the whole of Z. Similarly, the group Z is also generated by 2 and 3. So if we take the subgroup of Z generated by 2 and 3, it must contain 3 minus 2, which is 1, and then it must contain the whole group of integers, because of the previous example. So in general, two general remarks. If some subset X of G generates G, and Y is a subset of G which contains X, then Y generates G. Second remark, if some X generates G, and Y is a subset of G such that X belongs to the subgroup generated by Y, then Y generates G. Now let's talk a little bit about motivation. So let G be a group, and let X be a subset of G which generates G. Question: is there an easy and useful way to describe the whole group G in terms of this generating system X? And today we will give some version of an answer in terms of certain relations which the elements of X should satisfy. And terminology, all this together, generators and relations, are usually called the presentation of this group G, or definition of G using generators and relations. And this is usually denoted: G is given by the generators X and a certain set of relations. We will talk about this later during this lecture. Before we can do that, we need to talk about free groups. So let X be a set. Definition: a free group over X is a pair which consists of a group F and a map I from X to F, and this pair is supposed to satisfy the following condition: for any group H and any map F from X to H, there should exist a unique group homomorphism phi from F to H such that F is equal to phi composed with I. In other words, the following diagram must commute. So we have our X, and then the map I to F, and then we have H and the map F from X to H, and there should exist a unique group homomorphism phi from F to H such that this diagram commute. Let us note that directly from the definition, we do not know whether free group exists, and if it exists, whether free group is unique or not. So we know nothing about existence and we know nothing about uniqueness. And also a short comment about terminology. So this condition, which we have in the definition of the free group, it's an example of the so-called universal property. So free groups are objects which are given by certain universal properties. And for free groups, it's this one. So first, let us talk about uniqueness. Proposition: assume that we have two free groups over X, f, I and f prime, I prime. Then there is a unique group homomorphism phi from f to f prime such that I prime is equal to phi after I. Proof: by definition, since f is free over X, there is a unique group homomorphism phi from f to f prime such that I prime is equal to phi after I. Also, f prime is free over X, so there is a unique group homomorphism phi prime from f prime to f such that I is equal to phi prime after I prime. So if we put this together, we in particular have that I prime is equal to phi after phi prime after I prime. But we also can write that I prime is equal to the identity on f prime after I prime. And because of the uniqueness requirement in the definition of the free group, it follows that phi after phi prime should be equal to the identity on f prime. And because of the symmetry of the situation, phi prime after f should be equal to the identity on f. But this means that phi is an isomorphism. And this completes the proof of this proposition. Now let us construct free groups. So we will prove that free groups exist. So here is construction. If X is the empty set, then the group consisting just of one element, the identity element, is a free group over X, and the corresponding I is just the empty map from the empty set to the singleton. So let's construct free groups for non-empty sets. So let X be a non-empty set. Consider a disjoint copy X inverse of X, which consists of the elements X inverse for each element X in X. So we have an X and another disjoint copy when we mark all new elements by inverse sign. Let A be the union of X and X inverse. That's a disjoint union by definition. Consider the set A star of all finite words over the alphabet A. So we have all finite words where letters are either from X or from inverses to X. Note that this also includes the empty word epsilon. This is a word with no letters of length 0. Let us call two words in A star equivalent, provided that they can be changed one to the other by a finite number of insertions or removals of fragments of the form x inverse or x inverse x, where x is an element in X. So for example, the word A inverse BAC is equivalent to ABAC because we can remove A inverse. In turn, ABAC is equivalent to ABC inverse CAC because we can insert C inverse C. So the first word A inverse BAC is equivalent to AB C inverse CAC. So this defines an equivalence relation on A star, and we define the free group over X as the set of all equivalence classes in A star. For a word in A star, we denote the equivalence class which contains this word by this word and then overlined. Recall that we can concatenate words. So if we have two words, we can write one of them after the other. So if we have words V and W in A star, we have the word VW, V written to the left of W. It's also a word in A star. and we define our group operation on the set of all equivalence classes using concatenation of words. So if we have an equivalence class of V and an equivalence class of W, we multiply them by concatenating V and W and then taking the equivalence class. Note that in order to make this definition, we pick a representative in each equivalence class. So in order to say that this is well defined, one has to check that this does not depend on the choice of a representative in an equivalence class. So that's a check which one has to do. And then we can make the claim that this set F with this operation and with the class of the empty word as the identity element is a group. Proof. Concatenation of words is obviously associative, so our operation is obviously associative. If we take a word and write to it, concatenate it with the empty word on any side, we get our word back. So the class of the empty word is clearly an identity element with respect to this operation. And also, if we have some word x1, x2, and so on xk, and we concatenate it with xk inverse and so on, x2 inverse, x1 inverse, then we can remove xk, xk inverse, then xk minus 1, xk minus 1 inverse, and so on. We remove it all the way, and we will get the class of the empty word, which is the identity element. So this shows that any class has an inverse class. So there is an inverse element for each element in our group. This completes the proof of our claim. So the thing which we constructed is indeed a group. Now let us check the universal property. We claim that this is indeed the free group on X. So we define the map iota from X to F by sending an element X to the equivalence class of the singleton word X. And the claim that F, iota is a free group over X. Proof. Let G be a group, and let F be some map from X to G. We can extend the map F to X inverse by defining f of X inverse is equal to f of X inverse for any x in X. Now let us define phi from F to G as follows. If we have a word x1, x2, xk, we send it to the product of f of x1, f of x2, and so on, f of xk. Let us note that f sends the segment x inverse to f of x inverse, which is the identity, and similarly x inverse x is sent to the identity. And this means that our map phi is in fact constant on the equivalence classes in A star. But then it induces a map from F to G, because F is just the set of equivalence classes. And of course it's easy to check from the definitions from this formula that this is a group homomorphism. And uniqueness of this map is obvious. And this completes the proof of our theorem. So we have managed to construct a free group over any set X. Here is an example. Consider the set X, which consists of one element, little x. Then our alphabet A consists of this little x and its inverse. Further, the set of all finite words over this alphabet consists of all finite words in X and X inverse. Let us denote by n of W, where W is a word, the difference between the number of x's which appear in W and the number of X inverses which appear in W. Note that inserting or removing x inverse or x inverse x doesn't change this n of W, so it's an invariant of an equivalence class. And now we can produce a canonical form. So if we start from some word W and we remove all x inverses and all x inverses x's until we don't have any of them anymore, the final thing will have one of the following three forms. It might be an empty word if n of W is 0. it will be a collection of x's if n of w is positive, and then the number of x's will be n of w. Or it can be a collection of x inverses if n of w is negative, and then the number of x inverses will be minus n of w. So theorem, mapping a word w in A star to n of w gives us an isomorphism from the free group on one element x to the additive group of integers. So the additive group of integers is indeed a free group on one element. Proof. It's clear from the definitions that n applied to the concatenation of v and w is equal to n of v plus n of w. So our map is indeed a group homomorphism. And this homomorphism is obviously surjective. For any integer, we can produce a word which is mapped to that integer. From the previous slide, for example. On the previous slide, we saw that each element in F is equivalent to either epsilon or x to the power n or x inverse to the power n for some positive n. But all these elements are sent to different elements in Z, and therefore our homomorphism is injective. So we have a homomorphism which is both surjective and injective, so it's an isomorphism, and this completes the proof of the theorem. So the additive group of integers is the free group on one element, with one generator. It's a nice exercise, by the way, to show that the free group f of x is generated by x. Some comments on general free groups. First of all, if x is a non-empty set, then f of x is an infinite group, always. If the cardinality of x is greater than 1, then the group f of x is not abelian. And these non-abelian free groups are really complicated objects, they are quite hard to work with. All these non-abelian free groups are large in a certain sense, in the sense that the number of their elements grows exponentially with the length of the word. If we increase the length of the word in the canonical generators, the number of elements in the free group which can be expressed by words of those lengths grows exponentially. They're quite large. All non-abelian free groups have trivial centers. That's a claim which requires proof, and it's a little bit non-trivial claim. And even more, subgroups of free groups are free. That's quite a hard statement, which also requires proof. We are not going to use it. So, why are free groups interesting? And this is explained by the fact that any group is a quotient of a free group. Let's look at this in detail. So let G be a group and X a generating system of G. For example, we can take X to be equal to G. Then the subgroup of G generated by X coincides with G, that's the definition. Let us consider the free group F over the set X. By the universal property of this free group, there is a unique group homomorphism phi from this free group f of x to G, which is identity on X, so which sends each X to itself. The image of phi is a subgroup of G containing X, and since X generates G, the image of phi is G. So now we have a group homomorphism from a free group f of x to our group G, which is surjective. So by the first isomorphism theorem, G is isomorphic to the quotient of f of x by the kernel of phi. Now we can talk about presentations. So let G be a group and X a generating system in G. We just saw that in this case G is isomorphic to the quotient of the free group over X by the kernel of the canonical homomorphism from this free group to G. Let Y be some generating system in the kernel of phi. Then a presentation of G consists of these two sets, a generating system X in G and a generating system Y in the kernel of phi. And the elements of Y are called relations. Sometimes, instead of just taking an element Y in this set of relations, one writes it as Y is equal to the identity in the presentation. And sometimes, even more complicated, instead of talking about an element y in y, one writes that y times u is equal to u for some element u in the free group. So one expresses an element in the form of a certain relation. To get back to your element, we should multiply with u inverse and get that this element y should be equal to the identity in the quotient f of x modulo kernel of phi. Please note that presentations are not unique in any shape or form, even if we fix the generating system x. Really, by definition, this y can be any generating system in the kernel of phi. Here are some examples. Example 1. The free group f of x has presentation which is quite trivial. The generating system is x, and there are no relations. Example 2. A special case. We know that if x is a singleton, consists just of a, then the corresponding free group is the additive group of integers. So this means that the additive group of integers has presentation consisting of one generator and no relations. Example 3. Consider the quotient of the additive group of integers by its subgroup consisting of all integers divisible by some integer n. This is usually denoted by Zn. So this group has presentation which consists of one generator, let's say a, and one relation, a to the power n. Or we can write it a to the power n is equal to the identity. Indeed, the subgroup of all integers divisible by n is generated by this integer n, and we can write this integer as 1 plus 1 plus and so on n times. Therefore, if we send a to 1, the element a to the power n gets sent exactly to this generator, so that's the relation which we have to impose to have this quotient. So the kernel of our phi should be generated by a to the power n. Let us now briefly talk about applications of presentations. So the main utility of presentations can be summarized in the following statement. Theorem. Let G be a group with some presentation with generators x and relations y. Let H be any group and let F be a map from x to h such that for any element y in our set of relations, if you write y as x1, x2, and so on xk, f of x1 times f of x2 times and so on times f of xk inside H is equal to the identity. So all relations are sent to the identity. Then there is a unique homomorphism psi from G to H such that psi coincides with F on all generators. Proof. So by definition we know that our group G is a quotient of f of x by the kernel of the canonical map, and that this kernel is generated by the elements in Y. By the universal property of x, there is a unique homomorphism psi from f of x to h, which sends the element x to f of x for each x in x. By assumption, psi of y is equal to the identity for all y in y. Okay, this is our assumption here. Hence, psi of w is equal to the identity for any w in kernel of phi, because y generates the kernel of phi. And so we can define our map psi at the element phi of w as follows. So we define psi of phi of w as psi of w. And then this gives a well-defined homomorphism from G to H. And of course the uniqueness is clear because we define a map on generators. If we define something on generators, it's automatically induced on all other elements in a unique way. So this completes the proof of our theorem. Here is an example. The group of integers is generated by 2 and 3. Note that this generating system is minimal in the sense that no proper subset of it generates z. So 2 generates even integers and 3 generates integers divisible by 3. So let us try to determine a presentation of z in terms of this generating system. So what are the relations which are satisfied by these generators? Of course, there is an obvious relation that 2 plus 3 is equal to 3 plus 2. They commute. But here is another relation. 2 plus 2 plus 2 is equal to 3 plus 3. So our claim is that the group G, which is given by the following presentation, so you have two generators A and B, and the relations A and B commute, and AAA is equal to BB. This group is isomorphic to Z by sending A to 2 and B to 3. Proof. By the universal property of free groups, we have a unique homomorphism eta from our free group to Z, which sends A to 2 and B to 3. This homomorphism is of course surjective, as 2 and 3 generate Z. And the kernel of this homomorphism contains both AB A inverse B inverse and AAA B inverse B inverse. Let us estimate the size of the quotient of the free group modulo this kernel. Modulo the commutativity relation, we can write any word in the free group in the form a to the power I, b to the power j for some integers I and j. Modulo the relation b squared is equal to a cubed, so we can substitute any b squared as a cubed. We can now write any word like this in the form a to the power I, no b's, or b times a to the power I for some integer I. However, if we look only at these elements, the images under eta are all different. So a to the power I goes to all different even numbers, and ba to the power I goes to all different odd numbers. So all these elements are different in the image, so they are also different to begin with. And this means that the quotient of the free group by the kernel of eta is indeed isomorphic to Z by the first isomorphism theorem. Now let us briefly discuss finitely generated groups. So let G be a group. Definition: this group G is called finitely generated if it has a finite generating system. For example, any finite group is obviously finitely generated because it's generated by itself, and that's a finite set. Example 2. The group Z is finitely generated because it's generated by the element 1. It's an infinite group, but it is finitely generated. A negative example: the group Q, the additive group of all rational numbers, is not finitely generated. Indeed, if we take a finite set of rational numbers, then we will only have finitely many prime divisors in the denominators of those rational numbers. And when we add and subtract rational numbers, we cannot create new prime divisors in the denominators. But for all rational numbers, we should be able to have any prime divisor, and there are infinitely many prime numbers, so this gives us our contradiction. And finally, let us talk a bit about finitely presented groups. So let G be a group. Definition: G is called finitely presented if it has a presentation in which both the generating system and the set of relations are finite sets. Remark: any finitely presented group is automatically finitely generated. And proposition: any finite group is finitely presented. So, any finite group is finitely generated. So we can take G to be a finite group, and we can take as the set of all generators just the set G. So we consider the free group f of G, and we define Y in f of G as a set of all three-letter words of the form A times B times AB inverse. So here A and B are elements in G, and A times B is also one element in G. So this is a three-letter word. And of course, since G is finite, there are finitely many such words. And it's easy to check that this presentation indeed gives us our group G back. And that's a finite presentation. So any finite group is finitely presented. So some concluding remarks. Any finitely generated free group is finitely presented, because free groups don't have relations for the canonical generators. Remark 2. There exists finitely generated groups that are not finitely presented, but unfortunately the corresponding examples are quite technical and rather extensive. And the final remark 3, finitely presented groups are nice in the sense that after fixing a finite presentation of such group G, construction of homomorphisms from G reduces to verification of a finite number of equations. So our presentation gives us finite number of generators and finite number of relations. We send generators and we need to check only finite number of equations, and this can be usually done using a computer. So finitely presented groups are good because one can write computer codes to work with them. Some problems and questions at the end. Problem question 1. Prove with all details that if X generates G and Y is a subset of G such that X belongs to the subgroup generated by Y, then Y generates G. Problem question 2. Show with all details that the singleton group is the free group over an empty set. Problem question 3. Check with all details that the group operation in the construction of a free group is well defined. Problem question 4. Check with all details existence of inverses in the construction of the free group. And problem question 5. Check with all details that defining psi of phi of W as psi of W gives a well-defined homomorphism from G to H in the application of presentations. Thank you very much and see you next time.